All right, so now that you know how to make free body diagrams, we're going to learn how to apply Newton's second law, which is sometimes abbreviated N2L. We're going to learn how to apply that to problems. So first, a quick reminder. If you know the mass of an object, you can find its weight. So in this problem here, you are told it's 12 kilograms. That's the mass. You want to know what is the weight. The weight is the force of gravity. So remember, the force of gravity is always the mass times g when you are on Earth. So if you know the mass, you can find the weight. You multiply it by g. So in this case, here's the mass, multiplied by 9.81, and there's the weight. The weight of the shot put is 118 newtons. Okay? Also, because of this relationship, if you know the weight, you can find the mass. So if the weight is 450 newtons, you can find the mass of the person. So if F of g, the weight, equals m times g, and you want to find the mass, you divide both sides by g. Therefore, the mass will be the weight divided by g. In this case, that's 450 newtons divided by 9.81 meters per second squared, and you get 45.9 kilograms. So sometimes when you're solving a problem, you might think you don't have quite enough information. But if you know the mass, you can find the weight. All right? Okay, so what we're going to do now is apply Newton's second law. You've done free body diagrams, you've practiced a bunch, and you can draw free body diagrams. So what does it mean to apply this principle? Because Newton's second law is really a principle. So suppose we have two forces acting on an object. We have an applied force to the right, and we have a drag force to the left. What does it mean to apply Newton's second law to this problem? Well, remember, this thing here is called the net force. The net force is the unbalanced force. So the unbalanced force will be the difference between these two forces. So it is always true, and you can put this in your toolbox. It'd be a good thing to put in. For horizontal problems, when you are applying the net force to find the unbalanced force, you always take the forces to the right, because that's the positive direction, minus the forces to the left. That's the negative direction. Okay? So when you are applying Newton's law to horizontal problems, it's forces to the right minus forces to the left. For this problem, that means we take the force to the right, Fa, minus the force to the left, which is Fd. And so the net force for this problem will be written Fa minus Fd. That's the net force. Okay, so that's a horizontal problem. What if you had a vertical problem? Suppose I have a tension, F of t, going up, and I have a weight, F of g, going down. What does it mean to apply Newton's law to this problem? Well, for vertical problems, when you apply Newton's law, you take the forces that are going up minus the forces going down. So pause the video and take a minute to write that down in your toolbox if you want. When you apply Newton's second law to vertical problems, it's always the forces going up minus the forces going down. For this problem, that means F of t minus F of g. So when I apply Newton's law to this particular problem, I would get the expression F of t minus F of g. Okay? So let's see how that works in a real problem. Here we have two horizontal forces acting on a 500 kilogram boat. The engine exerts a forward applied force of 12,500 newtons, and the resistance of the water, which is called the drag force, exerts a backwards force, which is unknown. We know the boat accelerates at positive 2 meters per second, and we want to know what is the drag force on the water, on the boat. So we start with a free body diagram. Here's my boat. I know gravity pulls down on the boat, so I draw that force and I call it F of g. But the boat is not sinking. And in fact, we don't really care about the vertical forces. But the upwards force in this case would be a buoyant force on a boat, and that's F sub b. Now, these two forces are the same size. They cancel. There is no unbalanced force vertically. So we are worried about the horizontal problem right here. Okay? To the right, we have an applied force due to the engine. So I'll call that F sub a. And we have a backwards force, which is the drag force, which I'll call F of d. That's the drag force. And I'm going to make the force to the right bigger because I know that the boat is accelerating to the right. So it has a positive acceleration. Okay, so I know this force to the right is bigger than the drag force to the left. Now that I'm not going to worry about the buoyant force and gravity force because they cancel each other. We're worried about the horizontal forces in this problem. So my variable list is going to be the applied force, F of A, the drag force, F of D, which I do not know, and then I need the mass and the acceleration, both of which are given. Okay? So here we're going to apply Newton's second law to the horizontal problem. Newton's second law is a principle. It's an idea. It's not an equation. It's an idea that allows you to build an equation. So when I apply this principle to the horizontal problem, I'm going to get the forces to the right minus the forces to the left. So the force to the right is F of A. The force to the left is F of D. So when I apply Newton's second law to this particular problem right here, I get this expression. So what I've done is I've taken the principle, I've applied it to my problem to get an equation, and now I can solve this equation for F sub D, the drag force, which is what I'm after. Okay? So to get F of D by itself, I'm going to subtract F of A from both sides. That looks like this when I subtract F of A from both sides. Now, I don't want negative F of D, I want F of D. So I'm going to multiply both sides by -1. If I multiply this by -1, it becomes F of D. If I multiply this by -1, it becomes minus MA. And I multiply this by -1, it becomes positive FA. So there is my algebraic solution. I can plug in my numbers and run it through my calculator, and you'll get a result of 11,500 newtons. So that's how we apply Newton's second law to a problem to build ourselves an equation, which we can then solve. So you're going to solve a bunch of problems that involve horizontal forces, and this is how you do it. The next example involves vertical forces, and if you want to wait until you get to those problems to watch that video, that might be helpful. All right, when you're solving a problem with vertical forces, you're going to do the same kind of thing. We have a crane pulling upwards on a 400 kilogram air conditioner unit. It's a cable, so we're going to use a tension, and it's accelerating upwards at 1.2 meters per second squared. We want to find the weight of the AC, and then we're going to determine the tension in the cable. So here is my air conditioner. Here is the force of gravity acting on it. If the problem takes place on Earth, you are always going to have gravity pulling down on it. We'll label that F sub G. Now, it says the cable is pulling upwards on it, and it's accelerating upwards. So there's an upwards force on this. It's a tension because it's a cable, and it's got to be bigger than the weight. So this arrow here has got to be a little shorter than that arrow because we know it's accelerating upwards. So the net force must be pointing upwards, the unbalanced force. Okay? Those are all the forces we have. So we make a variable list. We have F of T, which is unknown. We have F of G, which we don't know, but we do know the mass and we do know the acceleration. So your variable list will always be the forces and M and A, because F equals MA is the idea. Okay? All right, so that's all I know. Can I find the force of gravity pulling down on this? Well, that was back what we learned earlier. If you know the mass, you can find the force of gravity. So we're going to first of all find the force of gravity, which equals m times g. That tells us the force of gravity. If you take this mass, 400 kilograms, and you multiply it by 9.81, you're going to get a force of gravity is 3,924 newtons. Okay, so that's the force pointing downwards. Now, we are going to step 2, apply Newton's law to the vertical problem. When we apply Newton's law to a vertical problem, we take the forces up minus the forces down. So the forces going up are F of T, minus the force going down is F of G. So when I apply Newton's second law to this problem, this is the equation I get. The net force, Ft minus Fg, equals the mass times the acceleration. And we're going to try to solve that mess for F of T, the tension. So we're trying to get F of T by itself. So since F of G is subtracted from the left side, we're going to add it to the left and the right side to get our solution. So if I add F of G to both sides, I get a solution F of T, the tension, equals MA plus F sub G. I can now plug in my numbers. I know all those things, the mass, the acceleration, and F sub G. And when I plug in all those numbers, I get 4,404 newtons, which I can write with three significant figures like this. And that answer makes sense because the upwards force must be bigger than the downwards force. If the downwards force, the weight, is 3,924, the upwards force needs to be bigger than that in order to make it accelerate upwards. So you're going to solve some problems with some vertical forces too in the problem set. Okay? All right, good luck.